A 6 kilogram object is attached to a spring and a string and a spring as shown below. When the 6 kilogram object is swung in a circle with a speed of 12 meters per second, the spring stretches a total of 5 meters, stretches to a length of 5 meters, the same length as the string. What is the unstretched length of the spring if the spring constant is 100 newtons per centimeter? Okay, so one thing I have to watch out for is that centimeters are going to have to be in meters at some point. Okay, so the idea here is this ball is swinging around. I think the length of this pole is 8 meters. So this is going to be 4 meters and this will be 4 meters, which means we have a 3, 4, 5 triangle here. So this is going to be 3 meters. And so the tension of the string is pulling it upwards and inwards, and the spring is also pulling it inwards, but then also downwards. And we also have gravity pulling it like so. This would be force gravity. Okay, and then I'm going to do force tension of this way. I do force string, but that's going to be confused with force spring, which will be force S. And each of these can be broken down into their X and Y components. And so that's what I'm going to do now. I'm going to look at it in terms of X and Y. X being horizontal and Y being vertical. So vertically, we're going to have, I'm going to call this force tension Y. And downwards we'll have force spring Y. And these are going to balance out because the ball is not moving up or down. So we know that force tension in the Y direction will equal force spring in the Y direction plus mass times gravity. And this is force times gravity right there, mass times gravity. So now I want to convert these into just force tension and force spring. And so I'm going to call this angle here theta, which is going to be the same as this angle theta here because they're similar triangles. They're just one is flipped over the other. They're both 3, 4, 5. And if we use that theta, we can say that to get the y, which is right here, that'll be the cosine of the angle. So force tension y is cosine of theta times force tension, which is equal to also cosine of theta. We're using this theta here, but they're the same, times force spring. We're going to also add in mass times gravity there, because gravity is helping out the spring pull the ball down. So now, I think that's good for that part. Now we want to look at it in terms of the x direction. So the x direction, there is an acceleration, but the acceleration is centripetal. So acceleration centripetal, which is v squared over r, the radius. And so the sum of all forces is going to be force tension x plus force tension spring, which is going to be force, I'll do little c for centripetal. And we do the same thing we did earlier, but this time we're going to use sine of theta. So force tension x is going to be the same as sine of theta. This is SOHCAHTOA. We'll probably do a little bit more of this later, I suspect, where sine of theta is opposite over hypotenuse, and it helps you calculate out which one to use. Force tension x is sine of theta times force tension plus sine of theta, same theta, well, different theta, but they're equivalent, times force spring x, there we go, equals mass, because we're going to do mass times acceleration, that gives us the force, and it's centripetal, so v squared over r. So now we know that r is 3 meters, since it's this length right here. We know v, because it was given in the problem. And we know the mass, so we know everything on that part. So we have two equations and two unknowns right now. So we can solve for one, plug into the other one, and then get what we want. So we're interested in the spring here. So what we're going to do is solve for force tension, plug it into this one, and then solve. I think that'll work. Let's go for it. So solving for force tension equals mv squared over r minus sine of theta times force spring, all divided by, actually what I'm going to do is I'm going to multiply this by 1 over sine of theta. Yep, and I'm going to distribute it. So this is going to be mv squared over r times 1 over sine of theta minus force spring. And this is what force tension is. I'm going to do this one. Actually, I'm going to simplify this a little bit more. I usually try and leave numbers till the end, but since we have so many numbers and it might be easier, we're just going to do this. So the mass is 6. That's supposed to be a 6. I know, it looks like a 4. 6 times velocity squared. Velocity is 12. Radius is 3. And then sine of theta. Sine of theta, as we talked about earlier, is opposite over hypotenuse. So the 1 over sine of theta will be hypotenuse over opposite. So the hypotenuse here is 5. So 5 over opposite, which in this case is 3. Minus force spring. We're going to do a little simplifying here. I'm going to call 12 squared to be 12 times 12. And I'm going to call one of these 12s to be 4 times 3. So this 3 is going to cancel with this 6 to give us 2. This 3 is going to cancel with that 3 just to be 1. And we're going to be left with 12 times 4 times 5 times 2. So 2, 12, 4, and 5 minus force spring. And that's going to be, I should be able to do it in my head. I can't. Well, I'm not going to. 12 times 4 times 5 times 2, 480. 480 minus force spring. This is probably 480 newtons. Okay, so now that we got that done, we can plug this in to this equation up here. So to do that, we're going to have black, very assertive. So cosine, very assertive. Cosine of theta times, now we know what force tension is here, it's 480 minus force spring equals cosine of theta times force spring plus, this is spring, plus mass times gravity. All right, so now we have one unknown in one equation. Divide everything by cosine of theta. And we'll try and move all the force springs over to this side over here. So we have 480 minus mass times gravity over cosine of theta, because we moved that over there, equals 2 times force spring. And then we're just going to divide everything by 2 over there. Light blue. So 480 divided by 2 is 240 minus mass times gravity over 2. I'm going to do this times 1 over cosine theta, just kind of separate out, equals force spring, and this is what we want. That's going to be our key to all of this. So putting some numbers in here, we have 240, which is 240, mass, which is 6, gravity, which is 9.8. Did I get gravity over here? No, because gravity is not involved in the x direction, only the y direction. Good call. I'm going to call it 10 though, just because I'm going to go with 9.8, more exact. Divided by 2 times cosine of theta. Now from our SOHCAHTOA over here, we know that cosine of theta is adjacent over hypotenuse, where adjacent is 4, hypotenuse is 5. So adjacent over hypotenuse. But then when we flip it, divide by cosine theta, we'll come with the 4 on the bottom. Yep, very nice. So do some simplifying here. The 2 goes away and this becomes a 3. Yep, so we have 240 minus 3 times 9.8, which is like 30, times 5, which is 150, divided by 4, which is like, I don't know, 40, so we have about 200. So 240 minus 3 times 9.8 times 5 divided by 4, you have about 203.25. 203.25. And that's the force of the spring pulling down. So now we know that force due to spring is negative K delta X. I'm not going to worry too much about the negative because that's just telling us direction. So we have 203.25, 0.25. Delta X is going to be the change in the spring. So the spring is pulling this way. So naturally the spring is shorter than what it actually is, shorter than 5 meters. So we're going to do 5 meters minus this delta X. That'll give us the unstretched length of the spring. So we know it's 100 newtons per centimeter. I'm just going to convert that right now. 100 newtons per centimeter times 100 centimeters per 1 meter. Cancel, cancel. So we have 10 to the 4th meters, or newtons per meter. So we have delta X equals 203.25 divided by K. And I just dropped the negative. So this is going to be the same as 203.25 divided by 100. And I just left the 10 to the 4th as 200s because it'll be easier to do this. Oh, and then so we have 2.0325 over 100. 1, 2, so 0.020325 meters, which I'm going to call 0.02 meters, which I'm going to call, 0.02 meters. Therefore, its unstretched value would be 5 meters minus 0.025 meters, which would be 4.98 meters. So it's unstretched means, because it's pulling, it's stretched a little bit, which means it's pulling against the direction of stretching, which means it's pulling down. And so its actual natural unstretched value would be less than 5 meters. So 5 minus 0.02 gives me 4.98 meters. And one of the things I also assumed here is that the spring is massless, because otherwise it's going to be probably pulling down as well. So we assumed a massless spring, kind of standard assumption, but you should probably be told that in life before assuming it. I just assumed it anyway. All right, hope this helped. See you next time.